Mobile salt, halite, in sedimentary basins can generate some really spectacular structures, but imaging these structures can be really difficult because the salt generates serious issues. Just consider the normal seismic velocity for sediments. So for siliciclastic sediments, let's take sand to sandstone, that will have a seismic velocity when it's deposited of about 1.5 kilometers a second, maybe 2. And with burial and lithification, that sand changing to sandstone will acquire eventually a seismic velocity of somewhere between 4 and 5 kilometers a second. Halite, from the moment it's deposited, because it's crystalline and has essentially no porosity, has a significant seismic velocity in this sort of range here, between 4.5 and about 5.2 kilometers a second. So for most of the burial history of a sedimentary basin, salt will have a higher seismic velocity than any sands that may encase it. And this velocity anomaly can create serious imaging problems. For well over 30 years, seismic companies have been trying to get around this to get better images of salt bodies, but more particularly the rocks that underlie them. These strata contain major oil fields in many parts of the world, so there's a prize there that's worth the effort. So in this short presentation, we'll be looking at some of the images that seismic companies are able to acquire these days by pushing imaging technologies. The images have come from their multi-client websites, where the seismic companies are demonstrating their technological capabilities. So consider this image created by CGG from the central North Sea, which shows a salt stock, salt dome structure. So this illustrates a legacy processing strategy, and notice the internal diffractions and reflections within the salt body itself, and the margins are rather obscure because of scattering effects caused by the high velocity salt in the middle of the image. Their reprocessing has yielded an image like this. And what you can see through their reprocessing is some spectacular detail, not only where you can image pretty much the edge of the salt body, but also the stratigraphic relationships of the sediments adjacent to the salt body. These positions can contain significant stratigraphic traps for hydrocarbons. Let's just zoom into the left-hand side. Here we go. So we can still see the edge of the salt stock through here, and there's some shadowing effects around the margins there, but you can still trace the stratigraphic sequences more or less up to the edge of the salt stock. So this is what modern seismic processing can do. Let's go to another part of the world here, to the Santos Basin offshore Brazil, and look at some images created by the seismic company PGS. This is a pretty dramatic image in its own right, but their challenge was to try and get an image of the deeper part of the profile just at the bottom of this image. So there's the salt body, and the economic target here is in the sub or pre-salt package that lies below. So there's an economic driver to get a better image down here so that drilling can target potential traps. Here is their enhanced processing, bringing out strata and potential fault structures below the salt. Notice also there's some pretty spectacular detail within the salt body now. So how have PGS and the other companies created these images? So the key is to get a really good model of the seismic velocities up through the whole package, which means understanding the salt geometry and the strata around them. So here is a seismic velocity model, where the red colours are high velocity and the blues and greens are low velocity. So although the seismic velocity increases with depth, there are important areas in here where the velocity changes laterally. Let's look at another example here from PGS. This is their seismic image that's been created. Again, notice the deeper part of the section, those little tilt blocks that are imaged below the salt. And here is the seismic velocity model that lies behind the seismic reflection image that we've just looked at, which you can still see in this velocity model. And just to illustrate the impact that having a good velocity model can make on a seismic image, so this shows another example from the PGS multi-client catalogue showing the geometry before processing using a high-resolution velocity model. Mission is to understand what happens below the salt dome, so that's the target. Let's see what happens. That's what happens if you apply a good velocity model. You can really bring out detail below the salt body. How does the reprocessing work? Well, it's an iterative process. From the initial seismic image, you create a velocity model based on the rock types you expect to form the geology, together with the anticipated seismic response. And on the basis of this velocity model, you create a so-called synthetic seismic response. In other words, you take the geometry and you create a model of the seismic image that would be created, tracing ray paths through the heterogeneous velocity structure. Then you can use those ray paths to remigrate the real seismic data, making multiple migrations, changing the synthetic, changing the velocity model a little bit, so you get better coherency between the final image and the modelled versions. It's a very elaborate and computer-heavy approach. Let's go and look at one of the frontiers for this type of work from the Gulf of Mexico. And it's this part of the world that's really been at the forefront of driving these technologies. Because just below the seabed, there's an amalgamated set of salt canopies that you can see in this really spectacular bathymetric map. And the economic targets are almost all below these canopies. Let's go and look at one example here from the Alaminos Canyon area. So here is a seismic velocity model produced by CGG, showing in the shallow areas there those blobs of orange which represent the high velocity salt. And that's overlying lower velocity normal sediments in green, but then those lower velocity sediments gradually pick up seismic velocity to the base of the section in here as the colours change green through yellow to orange through normal burial processes. So the challenge is to see through these canopies. Well, you get an idea of what they've done, because they've created an enormously detailed velocity model here. So that is the Alochnus salt canopy. So this shows some of their legacy data. This is still remarkably good imagery, but without a really comprehensive velocity model for the shallow part of the section and the salt. So having a really good velocity model and then changing the way in which the seismic data have been acquired, they're able to generate an image like this. So this image is created through a wide-angle seismic experiment involving multiple survey vessels that can separate the source and receivers to look beneath that salt canopy. That's really expensive, and the processing computer time is also really expensive and laborious. So why do they do it? The answer is in that large anticline that lies beneath and slightly ahead of the salt canopy, which is a significant play throughout the northern Gulf of Mexico. Offshore Texas and Louisiana, these deeper structures include oil fields such as the Atlantis and Mad Dog fields, which together probably hold somewhere in the region of 1 billion barrels of oil. So the prize is enormous. The drilling costs are also really high and can be quite hazardous. So there's a real driver to get excellent seismic imaging. So these combined technologies of acquisition and processing are revealing in great clarity the geological structure, even though the seismic velocity structure is really complicated. Getting these images involves complex migration strategies, iterated between the geology, the migration, and the velocity models. It involves creating forward models of seismic response, tracing ray paths that can then inform the processing workflow and the algorithms with which you can migrate the seismic energy. That, allied to new acquisition techniques, is providing these spectacular images in salt basins. And these images are completely changing the way in which we view salt mobility in sedimentary basins.